Welcome to the Researcher YouTube channel. My name is Jorge, and in this video I will show you how we can start with a simple model, add a controller, PID in this case, and since tuning PID controllers is quite challenging, how we can export our model as a simple FMU and then use some kind of optimization software for finding good values for our PID. First, I will start with the base case. I have a rotational inertia with a moment of inertia of just 0.1. Very simple. Then I have added a rotational damper with a damping constant of 10, a fixed point, and then a torque that will make our inertia rotate from the rotational sources package, and then a ramp. The ramp will start after 1 second with an offset of 0, and it will be increasing its value for 4 seconds all the way to a height of 100. Then we will set up our simulation. We will simulate from 0 to 10 seconds with an interval of 0.001. Remember to check on safe experiment annotation inside model and then simulate. We can plot the omega and we can see that we start from 0 and we go all the way up to 10 radians per second. Before I continue any further, I want to show you the software I will use for the optimization. I have used it in a previous video. I will leave a link in the description for it, but you can find it in the University of Linköping in Sweden. The name is Hobsan, and it's a tool that they develop at the university and they use for research, and they have different publications and so on. It has a lot of features, but in our case today we will use the optimization available there. Hobsan uses a quite special way of modeling. It's called transmission line modeling. I won't go into it in this video, but maybe in the future I will explain how it works, although it's very easy to find the explanation in the different topics in the user manual and the tutorials, and you can download it from their GitHub page, where you can find very good explanations on how to install it, build it, and so on. And if you find any issue, they answer quite fast, and there is plenty of topics going on. So for downloading it, I strongly recommend to download Hobsan with the compiler. Now, the model here is exactly the same as the one in Open Modelica. We have a rotational inertia with a moment of inertia of 0.1. In this case, the rotational inertia has the viscous friction included, exactly the same value of 10. Then you can see it has two connectors. On each side we need to connect one of these torque source. This one to the right is empty, it's just let's say closing the loop, but everything is set to 0, so it's not adding any kind of torque. and the one to the left takes the input from this ramp. This ramp has exactly the same values as the one used in Modelica. Now when I run it, you can see that I have the same simulation set up. And then here on the plot variables, we click on the angular velocity. And you can see that we go exactly the same from 0 to 10 in the same amount of time. My idea is to show you that even though the software is different, in this case it uses C++, we have exactly the same results. Now, back in Modelica, once that we have seen that we can run exactly the same model in a slightly different way, but in the end the same, I can move towards the control shaft example. The fixed point, damper and inertia are the same. However, I have added a speed sensor, and here I have a PID. The PID, the only value that I have changed is the upper limit output. This will be the maximum torque that we can provide to control our shaft. Imagine, for instance, some kind of electric motor or whatever. Then the PID needs the setup point. In this case, I use another ramp that starts after 1 second. It has a duration of only 1 second, and the height goes from 0 to 150. In this case, it will be 150 radians per second. Now the speed sensor gives the output to the measurement input signal of the PID. Now we can run it, in this case for 100 seconds. Again, we plot the angular velocity, and we can see that after a little bit of time, when the ramp starts, we require quite some time to go all the way to 150 radians per second. This controller is not very aggressive. It's usually desired for the controllers to be quite fast, so we can achieve the desired angular velocity way faster than this. Before I continue, if you want to see some examples using PIDs, you can go under blocks, examples and PID controller, where you can see a good example on how things work. But in this case, it's not interesting for me, but just so you know. To tune the PID, we would need to change values here. The problem is that changing those values, let's say by guessing or by hand, it's actually very challenging. So what I will do is I will export this part of the model as an FMU. Everything is the same. You can see that I have replaced the PID and the ramp by this real input that you can find in the interfaces of the blocks package, and the speed sensor is connected to a real output here. Then creating the FMU, it's very easy. You just need to export as FMU, and you will see down here in the message browser the path for finding the FMU you have created. Now, back in Hobson, I have already imported our FMU, but it's very easy. You go over here, click Import Functional Mockup Unit, and you just find wherever you have the FMU File, and click Open. In this case, it's giving me this warning because I've already generated the FMU, but you just import it and we compile it. That's why it's important to have the version of Hobson with the compiler installed. Now we have our FMU. You double click on it, you can see that we still have the important parameters that we had before. So we can change, if we need to do it, the damping constant or the moment of inertia. And now, to see that the behavior is exactly the same as this model, I just connect the ramp, run the model, and then you can see that our angular velocity is the same as for our FMU. Perfect. So what I want to do now, I will create an empty model, and now I have my FMU alone. If you remember here, we had a ramp going all the way to 150 after 1 second. So I'm gonna have the same in Hobson. Can use the filter over here. So our amplitude is going to be 150. We are going to start after 1 second, and our stop time will be after another second. So we apply, okay. Now we need our controller. So we can find under signal control, signal PID, we find our PID controller. Back in Modelica, you can see that our upper limit was 1500 and the lower is the same but with the sign changed. So we add those values. We need the reference value, we connect it. We leave the differential of actual value empty. We connect the actual value to the exit of our FMU. And the control signal, we connect it to the input of our FMU. And like in the Modelica case, we run our simulation for 100 seconds. However, we got this error. This error is related to having these kind of loops. By the way Hobson works with the TLM modeling method, we actually need a special component here. We need to remove this connection and add this component. So it was important to show this because if we go to properties here, we can see in the description that it adds a delay. However, the output will be exactly the same as the input. I will explain at the end of the video a little bit about the TLM method and why we need that delay. Now we run again and everything goes smoothly. We can plot the output of our component and we see that we get exactly the same as the Modelica version. We want now to make this transition to be way faster. For that, as happened in the Modelica version, we need to tune the PID. So we need to change the values over here. Since we are not using the differential part, I will only tune the proportional gain and the integral gain. So how do I do that? There's this option here that opens the optimization dialog. We click on the script wizard and we leave the options as they are because for the moment I just want to show how to use it. However, there is many optimization algorithms. You can test them and try to find the theory behind them. So we leave things as they are. I'm gonna reduce the number of iterations to just 50 to go a bit faster. And for instance, we can show the different plots. I will not export the data to a CSV file, we don't need it now. And these ones you can check them or leave them unchecked, but I'm gonna show what they do. Then we click next. So now it says that we need to choose optimization parameters. So what we want to tune are the KI and KP. So I'm going to choose two values for them, 100. These values, it depends on control system theory and so on, but for this example they work well. Now we click next, and now we want to minimize the difference between the input or the reference point and the actual output. So we want to make the difference between the ramp and the output of our FMU. We want to minimize it. We click add function, we leave the rest as it is, and when we generate the script, you see the code is generated for us, and then we just start the optimization. I don't want to save the current script, and then these windows appear. This one needs a few iterations to get started, but you can see our points, they are very spread. And then you can see this is the important. Okay, here we are. And this is the important window. You can see that our objective is becoming smaller and smaller. There are some cases where they are still quite big, and we are obtaining some values for the parameters and so on. And you can see how every run is completed and the total number of runs. So we just let it run and wait a few seconds until it's done. Here you can see how things are iterating and becoming better and better. So we will let it run for a few seconds. So our optimization is done, and we're going to check the values that are good over here. They are all very close to each other, so I'm gonna take just this one over here, the 6th one, and we click on apply. Then we can close these windows. You can see that eventually everything converges to a low value, and then we can click in our PID, and we can see that when we apply the values, they have been added here for us. Now apply and simulate, and we plot the output of our FMU. Now we can see that the very moment we start, in just a few seconds, we reach the desired value. So we need to apply those values now to our Modelica model. I'm gonna start with the proportional gain, and now take the integral gain. I have to warn you, there's going to be a little surprise here, but I will explain you why. We click OK, simulate, and then we check our speed sensor. You can see that there is a big difference from the result in Hobson and the results in Modelica. So as I said, there is a reason for that. If we open the PID, you can see here that the gains are over here. However, if I go back to the model, the parameter here is the time constant. So the proportional gain, this one we can leave as it is. However, this one we need to change a little bit. If we go to the code, check this unit time, we can see that this unit time has value of 1. So let's take a look to the equation again. Is 1 divided by Ti. So here we just need to do like this, and then we can run our model again. You can see now that we achieve the same result as the Hobson model. Before I finish the video, I just want to add a little comment. You can go to this translational mass. I'm gonna add it here, and you can check the code. You can see it's C++ code with the equations and so on. But if we go here to properties, we go to the description, I'm gonna make it as big as possible, we can see how the model is described. Here you can see the explanation. We start with Euler's laws of motion, and we transform this to the TLM boundary equations. The basis of the TLM is that all forces propagate in a way similar to waves, and since nothing can go faster than the speed of light, there's going to be a delay from the moment you apply the force to the moment that it reaches another point. So that is the basis of Hobson TLM equations. Thank you so much for watching, and see you in future videos.